This lesson is on continuity, section 2.5. Most physical phenomena can be modeled by continuous functions. Therefore, many of the ideas we will explore in calculus require continuous functions. But sometimes we have issues with continuity. There are two types of continuity. We can be talking about continuity at a point or continuity over an interval. Maybe the whole domain interval, maybe not. And the endpoints may be open or closed. All right, so definition, continuity at a point. Intuitively, f of x is continuous at a specific point where x equal a. If you're looking at a graph and you don't see any holes, any gaps, or any jumps in the graph of f of x. In other words, you can put your pencil and trace the graph of the curve without having to lift your pencil up at all. Otherwise, it's discontinuous at a. So that's the intuitive idea of continuity at a point. So we can use that idea if we look at these four graphs where we want to decide whether each graph is continuous or discontinuous at a point C. So this first one, you can see, you can put your pencil down on the graph, and when you go through C, you don't pick your pencil up, so that one's continuous. All right, the second one, there is a hole here, and there's a point here. So if you were going to take your pencil, you would have to pick up your pencil, put the point here at C, and then go back to your graph up here and continue. So this is discontinuous at C. And we're going to talk more about this later, but this situation, when you have a hole like this with a point underneath it, that's called a removable discontinuity. We will talk about how to tell if you have a removable discontinuity or not. Okay, this third one, we're just talking about continuity of a function at a point C. So intuitively, we can see that we do not have to pick our pencil up when we're graphing that. So this is continuous. And then here, if we were going to trace our pencil over this graph, we have to pick up our pencil, drop down here to this point, and then continue with our function. So this is discontinuous at C. This particular discontinuity is called a jump discontinuity. Okay, but we can't stay with just an intuitive definition of continuity. We have to have a formal definition, and this formal definition is very important. In fact, you will have to demonstrate the 3 points in this definition many, many times to prove a function is continuous at a point. So f of x is continuous at x equal a, at this point a, if and only if, number one, f of a has to exist. Okay, so a has to be in the domain. So you have to show that if this were 2, when you put f of 2 in, you get a number. So f of whatever the point x coordinate is, f of a has to exist. Second, the limit of the function at x equal a has to exist. So remember, you have to check the left and the right hand limit, and they have to equal, so that's the proof that the limit exists. So we have f of a exists, the limit of f of x as x approaches a exists. And then third, the limit has to equal f of a. And so this is known as the test for continuity at a point. So we'll be using that a lot. You have to memorize that. Okay, so page 14, let me show you what I mean by that. So it says use the test for continuity, those three conditions at a point, to determine why each graph is discontinuous at C and state the type of discontinuity. So the test for continuity and explaining why work together. So what we're going to do, step one, is we need to show that f of A exists. So this particular point is f of C. Now, this is not a real one because there's no real numbers, but you can see there is a point when x is C, y equals something, so f of C exists. And then step two, we have to show that the limit as x approaches C, the limit of f of x as x approaches C exists. Well, as you go from C to the left, you're heading here, and as you go to C from the right, you're headed there. So that exists. And then third, these two have to equal. Well, f of C is down here, and the limit of f of x as x approaches C is up here. So we can see that the limit as x approaches C of f of x does not equal f of C. And that's why we have discontinuity at C. So hopefully that starts to make a little more sense how we're going to use the test for continuity. It doesn't make complete sense because we don't have any numbers. Okay, and the type of discontinuity. So we can see that the limit as we approach, the limit of f of x as we approach from the left and the right is headed towards this point. So the limit exists. And so right underneath it, you've got this point. So the f of C does not exist here, but it does exist here. So when you have this whole situation, when you have a limit that exists from heading towards the same direction from the left and right, that's a removable discontinuity. And we'll talk more about that shortly. All right, this one, let's go through the test for continuity. Step one, does f of C exist? Well, here, clearly it does. When x is C, y is something, so it exists. All right, and then two, what about the limit as x approaches C? Well, the limit as x approaches C from the left is going towards that value, and the limit as x approaches C from the right is going towards that value. So the limit as x approaches C from the left and right of f of x does not equal. Therefore, the limit as x approaches C of f of x does not exist. And that's the reason we have discontinuity. So this is discontinuous at C. And this is called a jump discontinuity. Okay, so finally we have our real first example with actual functions and values. Okay, so we're given this piecewise function, and the first question is f continuous at x equal 1? To answer this question, you'd go through that test for continuity, so you just have to memorize it. So step one, f of 1. So when x is 1, that's greater than or equal to 0, so we're going to use this function. So we're literally just going to put 1 in, and f of 1 is 1, so f of 1 exists. Okay, step 2, we have to show that the limit as x approaches 1 exists. Well, 1 is not right here at this break, so 1 from the left and 1 from the right, you're going to use that equation, right? So the limit as x approaches 1 of x cubed is 1 cubed, it is 1. So it exists. the limit exists. All right, and then step 3, we see that f of 1 is 1, and the limit as x approaches 1 of f of x we just found is 1. So they equal each other. All right, so therefore, this function is continuous at x equal 1. But the next example is f continuous at x equals 0. Okay, so let's look at that. So step 1, does f of 0 exist? Well, according to this definition, when x is equal to 0, we're going to use the top equation. So f of 0 is 0, and it exists. All right, step 2, we need to show what's going on with this limit as x approaches 0. Okay, well, remember, you have to try the left and the right-hand side. So when you're going to 0 from the left, according to this piecewise function, you're supposed to use this bottom equation. So that function is -4. So the limit of -4 as x approaches 0 from the left is just -4. But the limit as x approaches 0 from the right, well, when x is greater than or equal to 0, you're supposed to use that top equation. And that's the limit as x approaches 0 from the right of 0 cubed, which is 0. Therefore, this limit as x approaches 0 of f of x does not exist. And so, this is discontinuous at x equals 0. Now, the type of discontinuity is up in the air. So f of 0 exists, but the left and right hand limit don't equal each other. So the removable discontinuity actually circled the wrong thing now that I've done this one. If the limit of f of x exists, then chances are you're going to have a removable discontinuity, but we'll talk more about it. Let's graph this and see what's happening here. So if I graph this from the 0 to the right, it looks like this cubic polynomial. This is what cubic polynomial looks like. So it looks like that when x is greater than or equal to 0. And then it looks like this when x is less than 0. And so you can see that this limit as x approaches 0 from the left is headed to -4, but the limit as x approaches 0 from the right is headed to 0. And you can see that that is a jump. So that's what caused me to remember I said the wrong thing there. When these limits, left-hand, right-hand limits are going into opposite directions, that's a good sign that that's a jump discontinuity. When this limit exists, that means that the left and right-hand sides are going in the same direction. So we usually get this jump of this removable discontinuity, which I still needed to give you an example of that. So I will, just a second. All right, so that is the answer to that. All right, now after we talk about discontinuity at a point, you get another definition, and it can get a little confusing because we're still talking about continuity, but this time we're talking about continuous functions over an interval, not just at one point, but over an interval. So the definition of a continuous function is not quite, it can be a little tricky. You really have to pay attention to the definition. And it is this: if a function is continuous at every point in its domain. So if you're given an interval to check or a domain to check, every point in the domain, if it's continuous at every point in the domain, it's said to be continuous. Okay, so the function in this previous example here, x equals 0, is in the domain. See, this is tricky because this domain doesn't have any gap in it. When x is 0, you use this equation, and so it's defined from negative infinity to infinity. And so 0 is in the domain, and that makes that a discontinuous function. Okay, however, so let's talk about why. Okay, so this is not a continuous function because the domain is not, the domain is negative infinity to infinity, and x equals 0 is in that domain, and it's discontinuous at that point. All right, so let me give you a weird example that will kind of bring home that this is not super easy to understand until you look at this example. So let's say I have this graph here. Let's say I have 2 here, and I have a function looking like this. Is that a continuous function or a discontinuous function? Okay, well, here's where your eyeballs, if they fail you. To me, it looks discontinuous. It's you're picking up your pencil, right? But by definition, see, 2 is not in the domain. So if we're looking at the interval on the domain of this entire function, the domain is negative infinity to 2 union 2 to infinity. So 2, it's discontinuous at x equal 2 because f of 2 does not exist. But this is, by definition, a continuous function. Why? Because it's continuous throughout the life of its domain. 2 is not in the domain, so you don't have to worry about it. So that is very tricky. So you really have to know your definitions. Okay, so the next thing, the following types of functions are continuous at every number in their domain. So if we know that polynomial functions, they have a domain of all real numbers, so they're always continuous. And here, this rational function, sometimes rational functions have a domain where you're having to skip over a number, but because we're skipping over the problem, the rational functions are continuous. So it's a little tricky. Root functions, square root functions are continuous. Trig functions are continuous. You might be thinking of tangent. Tangent has a domain issue, but since that domain, that values are not in the domain, it's a continuous function. Inverse trig functions are continuous. Exponential functions are continuous functions. Log functions are continuous. And this is important because we can just say, when we're trying to prove something, we can just say, well, I know it's polynomial, so I know it's continuous, when you're defending an answer or something. So that's what that's important about. Okay, back to this. So this is the discussion about removable discontinuities now. Okay, so there are types of point discontinuities. So we talked about them at the very beginning. Okay, so we have removable. Typically, there's a graph with a hole. Okay, so which means the limit exists. And so the reason we call this a removable discontinuity is because we can remove the discontinuity by redefining f at c. So let me make sure we write this down. So in a removable discontinuity is going to look like a hole, and you can always tell you're going to have, I won't say 100%, but if the limit of f of x as x approaches b exists, then probably going to be removable. So here is an example. So if we perform a little algebra on this, we can factor x squared minus 4 into x plus 2x minus 2, and then we have x plus 2. And so if you cancel that out, we get this function, f of x equals x minus 2, but x cannot equal negative 2 because you have to find the domain issues before you do any canceling. Okay, so if you remember from 171, that's going to show up as a whole. All right, so what we can do instead of, if I wanted to remove the discontinuity, I can redefine this function as f of x equals the function x squared minus 4 over x plus 2, as long as x doesn't equal negative 2, that function's fine. But when x equals negative 2, there's a hole there. So what I'm going to do is I'm going to redefine it as when x equals negative 2, well, let's let it equal something. What do we want to let it equal? Well, x minus 2 when x is equal to negative 2 is negative 4. So now I've removed the issue. The issue was at x equal negative 2. I removed the discontinuity. So that's why it's usually a hole. So this function here, it just looks like a line, except when you get to negative 2, there's a hole there. All right, so that's what this looks like. And what I did when I redefined it, what I did is plug the hole. That's why that's called a removable discontinuity. All right, this second one is something called an infinite discontinuity. And that happens anytime we have limits like f of x equals 1 over x. Now remember, this function looks like this. It's continuous over its domain. See, x is not in the domain. X equals 0 is not in the domain. But we're talking about point discontinuities. So if we're considering the point x equals 0, so the limit as x approaches 0 from the left is heading towards negative infinity, and the limit as x approaches 0 from the right of f of x is headed toward positive infinity. So those are indications that you have a vertical asymptote at x equals 0. So when you have any kind of vertical asymptote at x, then we'll call that an infinite discontinuity at the point x equals 0. All right, and the last one, we have a jump. Okay, so a jump would be like something at example 2b or 3. So 2b, you're jumping, and that's when the limit from the left and right are heading towards different values. That's a jump. This one right here, this is another jump. This one, even though it's not defined at 2, it's another jump, discontinuity. All right, and then there's something called greatest integer function. So if you have a function like f of x equals something like that, the symbol for that, so that's the greatest integer function. And the way that works is when x equals 1, it's 1. When x equals 1.1, it's 1. It's going to stay 1 all the way up till f of 1.99999. It's 1, and then finally when we get to a new integer, it jumps up to 2, so forth and so on. So greatest integer function looks like this. So 1. So when between 0 and 1, it's going to stay 0. And then when you get to 1, it's going to jump up to 1. And it's going to stay 1 until you jump up to 2. So that's what we mean by greatest integer function. Those are jump discontinuities. All right. Now, example 4 says, find all points of discontinuity and decide what type of discontinuity each one represents. And you have to always explain yourself. Okay, so remember the test for discontinuity? So 1, we have to show that f of a specific point exists. And so we know that f of x exists for all x because this function's domain is negative infinity to infinity. And in fact, we know f of x is a polynomial. And therefore, it's continuous for all x. So the previous page I said you want to know what the functions are continuous, so you can just state that. So there's not much work to do on that one. And then this one we have a little work to do. So we want to find all points of discontinuity. Okay, so the first thing we want to do is factor. All right, and after you factor, then the points of discontinuity are going to show up where the domain, for all numbers that are not in the domain. Why? Because of test 1. All right, so once you factor, then before you cancel, you know that x can't equal -5 and x can't equal 2, because we know the bottom of the fraction can't equal 0. All right, so we know that x equals, so then we can cancel, right? So f of x can be written as x plus 2 over x plus 5. So we know that it's discontinuous here because of point 1. F of -5 doesn't exist. F of 2 does not exist. Okay, but they exist in different ways. X equals 2 is discontinuous, but it is going to be a removable discontinuity. Okay, why? Because the limit as x approaches 2 from the left, if I just plug it into this reduced function here, is 4 over 7, which is 4/7. And the limit as x approaches 2 from the right is also 4 over 7. So the limit as x approaches 2 exists, even though f of 2 does not exist. So that's a removable. But x equals, in other words, there's a hole there. Remember, you cancel out, there's a hole. So if it's a hole, it's going to be removable. At x equals -5 is discontinuous. Because that is going to be an infinite discontinuity. And I can show you the limit, but first just remember that's going to show up as a vertical asymptotes. Factors that don't cancel show up as vertical asymptotes, but we could do this. The limit as x approaches -5 from the left would be -3 if you plug -5 right in there, and then -5 from the left is going to give you a small negative, so that's positive infinity. But the limit as x approaches -5 from the right is going to give you -3, a constant, over -5 from the right is going to give you a small positive, which is negative infinity. So the limit as x approaches -5 does not exist, and the one-sided limits are going towards positive and negative infinity, those are vertical asymptotes. So that's why that's an infinite discontinuity. Let's see what we got here. All right. So now we have a couple of examples that you might see. And it says find constants a and b so that the given function will be continuous at all x. Okay, so before you do anything, this is piecewise function. You want to look, of course, something is happening at 0. So you're using different functions as you approach 0 from the left and from the right. But also you want to just check to see where the domain restrictions are. All right, so first thing I'm going to do is, if I want to know what a and b is so that the function is continuous, I want to look at where we might have some issues, and I want to use the test for continuity. Okay, so first thing is when x equals 0, I'm supposed to use this. Okay, so f of 0, if I plug in 0, I get e to the 0 minus a, which is 1 minus a. All right, so in order for a function to be continuous, when x is 0, you're going to get a value, and that value has to equal the limit. So the next thing I'm going to do is I'm going to look at the limits from the left and the right. Okay, so as we approach the limit, as we approach 0 from the left, we'll use this one. So there's a lot going on this one, so I'm going to factor it. Okay, we get that, and then the x squared minus 4 factors into x plus 2, x minus 2. Right, so things are going to cancel, so I see that I have a hole at x equals 2, so I got to deal with the fact that x can't be 2, and these x's cancel. Okay, so I have to deal with the fact that x can't be 0, but here I am taking care of that. So when I finish all of this out, this function right here is just this, right? And I want this left-handed limit to equal the right-handed limit. Okay, so let's just write that down. So we're using the test for continuity. So we want the limit as x approaches 0 to exist. And in order for that to happen, the left-handed limit as x approaches 0 has to equal the right-handed limit as x approaches 0. Okay, and this left-handed limit is equivalent. This function is equivalent to x plus 2 because of the work we did here. So the limit as x approaches 0 from the left of x plus 2 has to equal the limit as x approaches 0 from the right of b. Okay, so I can use direct substitution here, and I can just put 0 in here, right? So that would be 0 plus 2, and this, the limit of a constant, is just that constant. And so we find out that 2 is equal to b. So now I know that b is 2, and I know that the limit, therefore the limit as x approaches 0 of f of x is equal to 2. Okay, so what do we have here? Step 1, we showed that f of 0 exists. We don't know what it equals yet. We're gonna. Step 2, we found out the limit of f of x as x approaches 0 equals 2. And remember step 3? These two things have to equal each other. So 1 minus a equals 2 when a is equal to -1. All right, so the limit as x approaches 0 of f of x equals f of 0 as long as a is negative 1. So it's a is negative 1, b is 2. Okay, so you're going to need this for web signs 2.51 and 2, the definition of point continuity from the right and left. So a function is continuous from the right at a number a if f of a exists and the limit as you approach x from the x equals a from the right of f of x equals f of a. So drew a little picture here. We're talking about point continuity. So right here, if we're looking at 1, f of 1 is equal to negative 2. It exists. And the limit of this function as we approach 1 from the right also exists. So this function x equals 1, this x equals 1 is continuous from the right. All right, here function f is continuous from the left at a number a if f of a exists. So if we look at x equals 3, f of 3 is equal to negative 1, so it exists. And the limit as you approach 3 from the left of f of x also equals negative 1. So when x is 3, at x equals 3, this function is continuous from the left. That's what this means. All right, but then again, we get this a little confusing when we get to a continuous function. So if we're looking at an interval and we want to know if the function is continuous, what we can say, remember, it's continuous if it's continuous at every number in the given interval. So if f is defined on only one side of the endpoint of the interval, so if I want to look at this interval here from negative 6 to negative 4, then we can say that this function is continuous on this interval. We don't really need to say the left and right. Technically, we would say at negative 6 is continuous from the right, but that's understood that the endpoints are only continuous in one direction. Okay, so if we look at this interval here, from negative 4 to negative 2, see how that's an open interval? So if we were talking about point continuity, it would be discontinuous at negative 4. But it's on an interval, so the function is continuous on this interval from the right. All right, so example 6, determine the intervals of continuity of f. Not point continuity, just the intervals of continuity. So basically that's just saying, well, the function is continuous on the interval from negative 6 to negative 4. And it's continuous from negative 4 to negative 2. And it's continuous from negative 2 to 0. And it's continuous from 0 to 1. And it's continuous from parentheses 1 to bracket 4. So really this is just, it's just verbiage, all right? So this function is continuous on these intervals. There are points of discontinuity in between those intervals, but it's just the language that we use. So it's not a big deal, this. And this one, number 8 here, you're going to need it for 1 and 2. So that's it for the continuity lesson.